Hey, this is me recording the class video because I can't get my Zoom working. So thank you for your patience, and hopefully this will be enough. Please get in touch if you need me to explain anything. I'll meet you in a working Zoom class at any time you want, and we can go over that stuff. All right, so our housekeeping slide to start. Once again, quiz 5 should be due next Tuesday. I might extend that just because of this situation, and it's time to start thinking about assignment 1. It is worth 10% of your mark, and it is due on June 18th, which is a Friday, at midnight. Now, the idea is there's 14 questions listed, but I only need 5, but they should all be on different topics, the topics that are listed at the top of the assignment. What I want you to do is clearly label the topic you're answering a question about. So if it's thermal equilibrium, I write thermal equilibrium, and question 7 deals with that, and show me all the work for full marks. You will lose marks if some parts of that are missing. You'll end up submitting that on Brightspace for me. To quickly look at quiz 4, where things went wrong. I mean, most people got it right, but I think this is question 5. What is the new area of a steel disc that is 5 centimeters in diameter? So remember, if this is 5 centimeters in diameter, this is an area question. So in order to do this, your original area must be pi r squared, so 5 divided by 2, right, to make a radius squared. And that goes into the formula. So I saw a few people picking 5.02 or 5.07 or whatever because they've used a diameter. So whenever it's an area, even if I give you a diameter, please remember to change it to area. The other one that people were getting wrong, classic number 1, everyone figured out the change in length correctly. However, temperature is dropping, so you have to do subtraction. So if you want to know what the new temperature, you take the original length and you have to subtract that change in length to get the new length. Other than that, it looked pretty good. Keep doing them. All right, today I'm going to talk a bit about specific heat and heat capacity. We're going to figure out how to find heat transfer from specific heat. So we're looking for Q again. And then we're going to use the formula to make a crazy calculation where we can mix two things together and figure out what temperatures they come to and get that thermal equilibrium figured out. Okay, so specific heat or specific heat capacity. Heat capacity has a variable of big C, and it's just talking about the ability of substances to store heat. So you can add heat without changing the temperature. How much can it eat before the temperature goes up, or how much can it release before the temperature goes down? When we talk about specific heat capacity, or specific heat, I'll say, that just means, and the variable is a little c, that's really kind of pinning it down, amount of heat that we need to change the temperature of a substance. So we're going to go say we're going to change it by 1 kilogram and raise that by 1 degree Celsius. Or we're going to change it, take 1 pound and raise it by 1 degree Fahrenheit. Okay? So if you have a good high specific heat, like water, the more heat you can absorb without changing your temperature. Okay? So think of cooking oil. Cooking oil rises in temperature very fast compared to like boiling water. It takes a lot longer. It goes up much quicker. And that's because it has a bad or lower heat capacity, bad or good. And likewise, if you think about water at the beach and the sand at the beach, the air temperature change is the same. I mean, there's other things that go into this, but the water can store that heat. It has a high heat capacity, so it doesn't change its temperature as quickly. So here comes another formula. Now, I'll usually use Cm delta T for both metric and imperial because I'm just like, whatevs. Okay, same, mass, weight. All right, notice we have many versions of how we can calculate it in metric. We can use joules or kilocalories or calories for heat. And if you are doing that, if you're calculating for joules, notice that your mass must be in kilograms. If you're calculating for kilocalories, notice that your mass must be in kilograms as well. And if you're calculating for calories, notice that your mass is in grams. So here it says mass in kilograms, but if you were solving for calories, you would use grams instead. Imperial is nice and straightforward. We get out BTUs, we put in pounds, and degrees Fahrenheit. So cm delta T, be using it quite a lot in the next couple of classes. Of course, this is something that's on your formula sheet. So here it is. Notice the nice thing about this one is you only have two choices. Either you're working in finding something in calories, heat transfer in calories, kilocalories, or BTU, and they all use the same values for C specific heat. So that's that symbol. Ignore the other stuff for now. That's coming next class. If you are calculating for joules, you have different and much higher and much more ridiculous numbers. And that's just the nature of the joule. Okay, so let's look down this thing and find what we see. So which one has the highest specific heat capacity on this table? Which one's a really good heat sink? Scrolling down, water. So water is an awesome heat sink. And notice that we have several phases of water here. We have ice and steam. So not only does your heat capacity depend on the substance, but also the phase of the substance, right? Water is a better heat sink than steam or ice, although they are still pretty good. What's the best metal heat sink? Just scrolling through it, looks like aluminum. So just kind of observing the different values, okay? These are also on the YouTube video. Just follow the link there, but I'm going to go through and do all the problems. Class problems, whatever. I'll move quickly, but you can pause and check stuff out. So the first question, how many BTUs must be added to 10 pounds to raise the temperature by 100 degrees Fahrenheit? So just writing, we're looking for the heat transfer, the BTUs. We know that the mass or the weight is 10 pounds. And this is a change in temperature, right? Raise the temperature by means it's already a change in temperature. So this one's pretty straightforward, 150 pounds. I'm sorry, 150 degrees Fahrenheit. So my formula, Q on your formula sheet, Cm delta T. Okay, so to find C, the specific heat of steel, I go over to the formula sheet. Now maybe I'll go back and look at that. I go to steel, which is with iron, and I'm making sure that I'm taking the value that corresponds to BTU per pound degree Fahrenheit. So 0.115. All right, so I'm going to write that down here as well. And it's just multiplication. Remembering I always use brackets to represent multiplication. (172.5 BTU. So you have to put in 172 BTUs to raise 10 pounds of steel from, whatever, 30 degrees Fahrenheit to 180 degrees Fahrenheit by 150 degrees. Next question, how many joules? So we want the gross number. Okay, and we have 500 grams, but I know the joules formula just from looking at the units on my formula sheet should use kilograms. So right away I divide 500 by 1,000 to get 0.5 kilograms. And I see a change in temperature. And once again, you can do T2 minus T1. You can just stick with hot minus cold. All you have to do is remember, if you produce a negative, it's cooling or you observe it. So I think I'm going to stay, just knowing where this lecture is going to go, I'm just going to do 75 minus 20 instead of 20 minus 75. Doesn't matter. And I'm going to get a change in temperature of 55 degrees Celsius. And I remember that it's being removed. Okay, so here we go. Look up the specific heat of water in joules. Here we go, come on. There it is. All right. So making sure you're in that joules column, the only one that uses those big numbers. 4190 is C. The mass is 0.5 kilograms because joules goes with kilograms, and the change in temperature is 55. do that multiplication, 115, comma, 225 joules. And that is cooling, so that is coming out of the water. Here's the one that were for you, now they're for me. So at any point, if you want to work on these, pause the video and just try it on your own. Instead of, the awkward time in class when we be doing it. Okay, here we go. We've got aluminum. I look up the C value. 4 pounds for the imperial system, and I see that it's going to be 0.22. And then it's right into the formula. Cm delta T, or Cw delta T. Same. 0.22, 1.5 pounds. Change in temperature is 40 degrees. It's already all worked out for me. Straight up multiplication. And it's a little piece of aluminum, so we don't need a lot of heat. 13.2 BTU. Here's a more complicated one. We've got kilojoules. Actually, I want to change this. I forgot to change this question. I want to change this to, because I changed phase by accident when I set this up. So let's change that value right there. And we are going to do the formula, except here we have the heat. So I already know Q is 23,000 joules. I want to work in joules because that's how I can find C. So I'm just going to build the formula with what I know. 23,000. And we're talking about water, so I know that the specific heat of water from the table is 4190. I know that, I want this to be in the mass, or the weight also to be in kilograms, right? Because kilograms go with joules. So I'm also going to convert that by dividing by 1,000 to kilograms. I'll write that up here. There we go. And I'm solving for a final temperature. So what I don't know right now is the change in temperature. So just warming up with a little bit of algebra, because we're going to have a lot coming up. 4190 times 1.5 is 6285. And I still don't know the change in temperature, so I'm just kind of writing it down in brackets to protect it. If I want to find out the change in temperature, I'm going to divide both sides by 6285, whatever's stuck in front of the variable I want to isolate. That will just get rid of this, and I will end up with 3.66 when I do that division as a change in temperature. Okay, so let's go back. What does the question want me to solve for? It wants a final temperature. So if I started, and just talk yourself through this, if I started at 10 degrees Celsius and I'm heating it, I'm adding 3.66 degrees Celsius. That's a change. I'm going to get to a new temperature of 13.66 degrees Celsius. So that's the actual answer. Next, we're going to take this formula into a bucket of crazy. So we refer to a lot of different ways. The method of mixture. So this is taking two substances at different temperatures, different masses, different specific heats, of course, because they're different substances, or maybe they're the same. And we put them together, and the rule is they will come to what we call thermal equilibrium. The temperature will be the same. And how we get to that same temperature is by one substance losing a certain amount of heat, which is the same as the amount of heat that the other substance gains. Okay, so of course there are some assumptions, no heat loss to the surrounding. This is a perfect closed experiment. But because we know that one substance will lose a certain amount of heat, which is the same as the other substance will gain, we can create a Franken formula and use that concept to solve for, equilibrium temperatures, the temperatures that they both come to. So here's a formula, and it is disgusting. So this is going to be, and I want you to set this up the same way every time. This is going to be the hot side, and I'll show you a trick to keep yourself straight, and this is going to be the cold side. And the L here means lost. So it's recognizing that the hot side is going to lose heat. And the G here means gain, so it's really confusing. You want to say liquid and gas, no, it's lost and gain. And that G is recognizing that the cold side is going to gain heat. Okay, so this is the initial temperature of the hot side. This is the initial, notice the positions of the cold side, they're not in the same location. And the final temperature that you're going to come to is here. So we're going to have an unknown on both sides of the equation. So let's work our way through a bunch of them. Okay, here's what I strongly recommend you do. Get yourself a table that looks like this. Make your own. Decide which one's the hot side. We've got iron at 350 and we've got water at 65. So the iron is the hot side. So I write down iron and I write down water. And this is just so I put all my information in the right place. Okay, specific heat. Over you go to the table. Look for the BTU, the imperial one, because we have pounds and degrees Fahrenheit. We know we're in imperial. Specific heat of iron, 0.115. Specific heat of water, 1. The mass or the weight of iron from the question, 0.5 pounds. The mass or the weight of the water, assuming that's just 10 pounds of water, not a water plus container. There we go. And the initial temperature, the beginning temperature of the iron is 350 degrees. And the initial temperature of the water is 65 degrees. And we're solving for the final temperature. So I'm going to call that X because I love algebra and I love X's. And my X's are going to be the unknown variable, not the multiplication symbol. And I'm just going to throw this out of the way here. Okay, so we know that hot equals cold. The heat lost on one side equals the heat gained on the other side. So I'm going to write down the whole formula one time, and then from now on I will ignore it. Just so you make sure you have it. Minus T final for the hot side, and then on the cold side, the temperature gained, T final. There we go. Okay, so what I'm going to do is I'm going to take all this information here, and I'm going to put it in this side of the equation. Let's go to black. Specific heat of iron. The mass of the iron. The original temperature of the iron. The equilibrium temperature of the iron, which will be the same as the equilibrium temperature of the water. That's my unknown. Specific heat of water on the right side. The mass of the water. The equilibrium temperature of the water, what it comes to is first. You cannot mix this up or you will not get the right answer. Okay, there's going to be some algebra. So let's start. I'm going to multiply this and this. Just clean up each side a little bit before we hit distribution. So that will be 0.0575. And I'm just going to leave these brackets for now. And then I'm going to go over to my left side, and I get 1 times 10, sweet, is 10, x minus 65. Okay, algebra number 1. So because this 0.0575 is smashed up against brackets, what I need to do is multiply it by everything inside the bracket. And the same with the 10. This is called distribution. So you might remember this. You might have blacked it out because you hate it. So if I do 0.0575 times 350, I get 20.125. And if I do 0.0575 by negative x, well, they can't really multiply, but they can just smash together. And on the right side, 10 times x, they can only smash together. And negative 65 times 10. So if you're struggling with this, check out some videos on algebra. Khan Academy is great. Or follow the method, right? Follow what I'm doing. Get used to it. Okay, next I need to put x's on one side and my numbers on the other side. So anything that has an x at the end, I want to gather together. So what I'm going to do is I'm going to take this one and move it over to the right side. And I'm going to do that because I want to gather and combine those two terms. So if I move it to the right side, it's going to become positive. That is just how it works. And at the same time, I'm going to do this in blue, I'm going to take the negative 650 and move it over to the left side, where it will become positive. So if you cross the equal sign, moving things that are added and subtracted, you must change the sign. It doesn't matter if you had moved x's to the left and numbers to the right. I just usually move things where they're positive because that's what I like. Okay, so let's clean that up. So I had 20.125. I didn't move that, but now I've moved 650 to the left side where it's going to be added instead of subtracted. And on the right side, 10x didn't move, but now I'm adding in this decimal. I can do this math. 20 and change plus that 650 will give me 670.125, and 10x plus 0.0575 is going to give me 10.0575x. Okay, so just adding up the numbers in front of the x's, don't make it x squared. The x's just stay the same. It's like 10 apples plus 0.0575 apples doesn't make 10.0575 apples squared. Here we go. Now we're going to divide both sides by that 10.0575, and you will get 66, the same as we were doing the other question, 66.6x. So what does that mean? Our final temperature of the mix, 66.6 degrees Fahrenheit. So both the iron and the water will end up at this temperature. Notice how close that is to the original water temperature. There's some factors. Water is that awesome heat sink, so you expect it to be able to absorb a lot of heat without raising its temperature very much. There's also a lot more water by mass than there is iron, so that's in play as well. So be aware of that. So the other thing I want you to remember is when you do these problems, your answer will be between 350 and 65. You will never get like a number higher than 350 or a number lower than 65, because the equilibrium will be somewhere in the middle. It might be very close to one of the temperatures, but it has to be between. And if you do this and you notice it's not in between, the chances are you've messed up one of your negatives in the algebra. Here we go again. So this time we have grams. As long as the units are the same, you can just work with it. We have cold iron and we have hot water. So we're going to put water on the hot side and iron on the cold side. And let's fill it in. Specific heat of water, if you're using grams, will be 1. Iron is the same as last time, 0.115. Mass of water is 750. So make sure everything goes in the right place. Mass of iron is 50. Original temperature of the iron is 20. Original temperature of the water is 80. And we're going to solve for the final temperature. Same. Hot equals cold. Put the hot stuff on the left side, the cold stuff on the right side. Okay. Water. Filling in. C, M. Original temperature minus equilibrium temperature, final temperature. And over we go to the iron. C, M. Equilibrium temperature minus the original temperature. Okay, cleaning up this multiplication. We get 750, prepping for that algebra, that distribution. And on the right side, sorry, we get 5.75x minus 20. We're going to multiply in the 750 to everything in the brackets. So you should have 4 new things after that. 60,000 minus 750x equals 5.75x minus 115. Okay, so what now? Now we move stuff around. I'm going to send this 750 over here. I'm going to send the 115 over to the left side, and remembering that will change the sign. So the 60,000 was already on the left side, but now I'm going to, instead of subtracting, I'm going to add 115. The 575 was already, x was already on the right side, but now I'm going to add 750x. Do the math on the right side, 60,000 plus 115. Do the math. Sorry, did I say right side? Do the math on the left side. Do the math on the right side. 755, adding up the numbers in front of the x's and just bringing the x along for a ride. Divide both sides by whatever's in front of the x, and you're going to end up with 79.5 degrees Celsius. So once again, temperature of the water only went down 0.5 degrees, and the iron shot way up. So that's that great water. Sorry, that slide cut off because I made a mistake on this slide and had to re-record it. Here we go again. So class practice 1. What are we mixing this time? Ooh, we're mixing water with water. So I know that I'm going to have water here. I'm going to have water here. And, oh, I have milliliters, but I see down here I have told myself that 1 milliliter of water has a mass of 1 gram. So what I can do is just change this to grams and this to grams. Okay, so last time I put the hot and the cold on the wrong side, so that's why I'm re-recording this. So let's see, our hot water is 76 degrees. So here we go, and that is my 550 grams of water. It's going to come to an equilibrium temperature, and water has a specific heat of 1. My cold side is also water, same specific heat, which means I could drop them in the formula if I wanted to. I'm taking 200 grams at 10 degrees, and it's coming to the same temperature as my hot side. So I'm going to drop the formula because this is a third time through. C also could be dropped, times the mass of the water, times the hot temperature, initial temperature, minus the equilibrium, the final temperature, equals, on the cold side, C times the cold water, 200, yep, times the equilibrium temperature, subtracting that original cold temperature. All right, so this number is just the same, so I'm going to distribute right away. 550 times 76 is 4,100, 800, and then it's going to be minus 550 times x, and on the right side, 200 times x minus 200 times 10 minus 2,000. Okay, I'm going to rearrange the formula. I am going to gather my x's on the right side, 200x plus 550x. I'm going to gather my plain old numbers on the left side, 41,800 plus 2,000, and I'm going to get 43,800 equals 255x. When I divide both sides by 255, I'm going to get x equals 8.4 degrees Celsius. So a little more in between because you're mixing water with water. They have the same specific heat. How would you know if you did your work right? You could check your answer in your formula. So what I'm going to do now is write a check. So taking that left side, is 550 multiplied by 76 minus 58.4 the same as 200 multiplied by 58.4 minus 10? So just going on, is 550 multiplied by, what is it going to be, 17.6 the same as 200 multiplied by 48.4? So just respect your order of operations. You're going to do that last multiplication and you get 9,680 on the left side, and you'll get the same number on the right side. If they're the same number, that means you did your math right, and 58.4 degrees Celsius is the correct answer. Last one. Okay, we've got water and we've got copper. The copper is hot and the water is cool. Okay, copper, we have 2.7 pounds and it's at 80 degrees. Hey, we got the final temperature. Okay, I'm going to write that in. the water is, okay, where is it? Half a pound, 0.5 pounds, tiny amount of water. And it is at 50 degrees to start and it ends at 60. So, I could look up the heat capacity, obviously, on the chart, but here it's telling me it's what it wants me to find with math, so I will put an X here, different unknown. And my water I will actually look up and maybe take a gander at what I should be getting for my answer. But here we go. Okay, so make your formulas, just put in your unknown where it goes. I don't know the specific heat of copper. Theoretically, I don't know it. The mass of copper. But this time I can do 80 minus 60. I have that temperature change. And on the right side, specific heat of water by the mass of water. And once again, equilibrium final temperature minus the initial temperature. So what I'm trying to figure out here is, I'll do it in baby steps, remembering that if it's in brackets, you do that math first. 0.5 times 10. And then I'm going to put the number first. 2.7 times 20 is 54, and then the X after, because that's how I like it. And 0.5 times 10 is 5. I divide 5 by 54. And I'm going to get 0.092, and then I have 5, 6, whatever, on the sheet, on the formula sheet, this is a specific heat of copper, but close enough because I just made this question up. All right, so that's 4 examples. I will also start next class with some more examples. What do I want you to know? I want you to understand a bit the concept of specific heat, that ability of a material to absorb heat, which is different than thermal conductivity, which is the ability of a material to allow heat to flow, which is different than the coefficient of linear expansion or volume expansion, which is the ability of a substance to dictate how much it will expand or contract when you change the temperature. So we're getting a lot of formulas and a lot of concepts. So really make notes to keep yourself straight. And then I want you to be able to find Q, the heat transfer, given specific heat and mass and change in temperature. And I want you to be able to set up and solve these thermal equilibrium mixture problems, which are, arguably the mathiest portion of the course. So if you can do these, that's awesome. Thank you for your patience with me this morning.